Hello, everyone. My name is Guoyu Lu, Assistant Professor in Imaging Science in RIT, and it's really my great pleasure to have Dr. Majid Rabbani to give us a talk today. And Dr. Rabbani has already been here for working in Rochester area, especially in Kodak, for more than 30 years, and he has been also in RIT for more than 5 years, I think, right now. And Dr. Rabbani is very humble. I just tell him he has worked here for 30 years or 35 years, and don't need to introduce many more. But I want to let everybody has attention that Dr. Rabbani is very well known in the area of imaging science, actually, and especially his contribution in JPEG and MPEG standard, and he has been a SPIE Fellow and IEEE Fellow for many years as well, especially Kodak Fellow. Actually, that is very prestigious honor for everybody working in Kodak. And together with Dr. Majid Rabbani, he's a Ph.D. student, persona ready, Curthy, and is also giving probably giving us some brief introduction of his work together with the Dr. Rabbani, and he's a PhD student of Dr. Rabbani. He has also been an intern in Microsoft as well. So let's welcome Dr. Majid Rabbani and his PhD student persona to give us the talk.
Thank you very much, Dr. Luo. It's a pleasure to be here, and thank you so much, all of you, for attending. Hopefully, you will find this presentation entertaining. So the presentation will be about super resolution, both the traditional, also known as computational or reconstruction-based algorithms, and the more novel deep learning or example-based approaches. And most of the simulations of the more recent work that you see here has been done by Persona. Some of the work, everything that you see here actually has either been downloaded from some software that you could repeat and reproduce those results yourself. So let me see if okay, very good. Let's start with the definition of resolution. I mean, it's good to know exactly what we want to talk about today. So resolution can mean different things to different applications, right? We today, by resolution, mean spatial resolution, which is pixel density in an image, could be measured as pixels per unit area or pixels per unit length, either horizontal or vertical. But some people might look into radiometric resolution, which is mostly like a tonal or a bit depth type of resolution, or temporal resolution, which is a number of frames, or a lot of people who work in the area of remote sensing within the Center for Imaging Science look at spectral resolution, that for a color image could just be the number of color planes, or could be the number of spectral bands for Landsat images, which could be in excess of 2,000. But as I said, in the context of this presentation, we really look at spatial resolution, and that's what we're trying to super resolve. So before we go further, we're going to be talking a lot about we have a 2x improvement in resolution, we have a 4x improvement in resolution. So let's see what perceptually does that mean. So in order for everyone with the Zoom connection to be able to see this dramatic difference in resolution, I had to pick a very low resolution image. So look at this 46 by 32 pixel image. You can hardly make any detail out. And if we improve the resolution by a factor of 2, which essentially means 2x horizontally and 2x vertically, meaning that every pixel is replaced by 4 finer pixels, then we get a resolution improvement of 2x. And you could see the perceptual difference. This is what we got when we went from, let's say, DVD to HD Blu-ray, or when we went from VHS to DVD, or when we're going from HD to 4K resolution. If we go another ladder up the resolution, 4x, which is again what DVD to 4K resolution would have been, you could see what a huge difference that is. So whenever I refer to a 2x improvement in resolution or 4x improvement in resolution, kindly remember this particular demonstration, and that's the level of improvement that we're talking about. So I'm going to play, and I don't know exactly how well this is going to play with Zoom, because we tried it yesterday and it was a little choppy. So, just be kind and patient. I have the actual link for you so that you can refer to it. This is the movie Blade Runner, okay? Harrison Ford playing. And the movie was released in 1982, but the scene of the movie is set, this is a sci-fi movie, right? The scene is set in November of 2019, which is not really that far back. And Harrison Ford is looking at a video and he's trying to enhance it in order to extract some information. And you're looking at a frame of that video right now where there is a mirror, and he would actually end up getting the face of a person from that mirror and then printing it in a hard copy print. So the wording, as you could see to the left, is enhanced 34 to 36, pan right. So we're going to see all that, and I'm going to play the video. Hopefully it'll play for you. Oh, sorry. It's, let me see. Let me do this one more time. I think we want to start at minutes 1:15. Now, remember, back in 1982, University of Southern California had just a few years before digitized a few images like Lena and Peppers and Baboon that most of us old timers are familiar with. I was still writing in Fortran, feeding cards into a computer at University of Wisconsin, where I was doing my PhD. So a lot of people consider this the prophecy for super resolution. You see that mentioned during some of the papers. 2 years after this, and then 20 years after that, there were two seminal papers that marked the beginning of what we call computational super resolution, and then what we call the example-based or the deep learning super resolution. So the paper by Tsai and Tom Huang, which was published in 1984, is widely considered to be the first paper that essentially made reconstruction-based super resolution possible. And they talk about fusing images together, registering them, and creating a high resolution image. As an aside, Dr. Tom Huang is probably one of the most influential people in the area of image signal processing from University of Illinois in Urbana-Champaign, and also computer vision. He was a professor emeritus. He became one in 1978, when he was 78 years old in 2014. By then, he still had students. When I heard about his retirement at the age of 78, it reminded me of the author, Scott Elledge's famous quote that it is time I step aside for a less experienced and less able man. He really continued his work even after that. And sadly, he passed away last year, but his legacy will, of course, exist for long. Nearly 2 decades after that, The paper by Baker, Simon Baker and Takeo Kanari at CMU marked the beginning of example-based super resolution. The paper was called Face Hallucination, okay? So I can't just really help it but imagine a typical conversation in the corridors of CMU, friends saying, hey, Simon, what are you up to these days? Face hallucination? Cool. I know exactly what you mean. You do? So this is an example of face hallucination, not the one that was reported by Simon and Takeo, but it's a more recent one that was done by super resolution generative adversarial networks. This is a 2017 version. It's much more impressive. As you can see, there's a 16x resolution enhancement from the paper, image of the face to the left, all the way to the super resolution GAN, which is to the right. This is another paper, and we will talk a little bit about this later, okay? You could actually see the presentation on YouTube. It's a CVPR presentation at this address. So what is the super resolution framework? Again, super resolution refers to obtaining an image at a resolution higher than that of the camera sensor, right? And there are two ways that you could do super resolution. One is from a single low resolution image. This problem is highly ill-posed because the low resolution version cannot contain the high resolution version, right? Imagine that I tell you, look at number 72 and tell me what two integers when multiplied together give me number 72. You say, well, there are so many different solutions, okay? And then I tell you, okay, let me regularize this problem for you a little bit. How about I give preferences to numbers that are closer to one another? And then you say, oh, okay, then maybe a good solution is 9 times 8, okay? So if you are looking at a problem that is ill-posed, like give me two numbers that but multiplied give me 72, you need heavy regularization. And with regularization, you can limit the number of solutions to something. But generally, the early work on super resolution was not super resolving from a single captured image. Rather, it was about super resolving a low resolution frame from a sequence of images that were taken, maybe 30 frames per second. And that problem, as we will see mathematically, is it still requires regularization, but it's much more tractable mathematically. So you could kind of see the difference between what we call the example-based algorithms, which are more the deep learning ones, and the old ones that look at frames of video, because the computational-based approach essentially looks at a sequence of frames, takes one that is low resolution, uses the information in all the frames to improve the resolution of the image. Whereas the more recent work, they take a single low resolution image, but then they train the network. That's a form of regularization. They train the network with many similar example images, and then try to super resolve a single image. We will discuss both, okay? But for now, computational or reconstruction-based super resolution essentially looks at the paradigm that I said. This is circa 2005. There is a company called Motion DSP. It was founded out of University of California in Santa Cruz, and I downloaded that from their website. They're a different company now, so you won't be able to download this image anymore, but essentially look at the 4 low resolution captures and what they create from those 4 low resolution captures. Neither of those low resolution captures contain the information that you see to the right. However, collectively, when computationally registered, deblurred, and with all the works, they actually create a very nice looking super resolved image. Theoretically, again, these are borrowed from Rossi Rubner's slides, because he gave a very nice presentation. You could download it from the web. These are all available. It's a very simple way to kind of build the case for why super resolution is possible theoretically. Imagine that I wanted to super resolve an image with the grid points that I'm showing you right here, right? Clearly, I need to sample it as many of those sampling points as you see using Shannon's sampling theorem. If I do not sample it adequately, for example, if I sample it like this, then clearly there is no way that I can reconstruct that image from the sparse number of samples. But now suppose that I had a perfect setting and I moved my camera, okay, to the right by exactly half a pixel. And then I took another picture. Then I moved my camera. This is a very controllable setting, right? I moved my camera down by exactly half a pixel and took another picture. And then down and to the right by half a pixel and took another picture. And then somehow I combined all of these pictures together, as you could see in the animation. Now, essentially, one can say collectively between the four pictures, I do have the information that might enable me to reconstruct that image at a higher resolution. But, you know, as the old saying says, climate is what we expect, weather is what we get, right? This is what we expect, but what we get is this. The camera displacement is arbitrary. The camera might rotate or shake, might get a little closer to the object. Things might move. So in practice, you actually will record something like this. And you're lucky if you could record something like that. And now you want to reconstruct at that location, which I have circled in red. You do see that there is information. However, the information is not as nicely available to you as you might have expected that. Okay, so what do? Well, all of these super resolution algorithms that are based on, again, what we call reconstruction based, are based on looking at a series of images. They all have to face this problem. This is a picture from a very nice review of super resolution image reconstruction in IEEE Signal Processing magazine in 2003. So this article is almost 18 years old. As you could see to the left, you can have a camera where multiple frames of a video could come to the camera, or the same scene can be captured by different cameras. Or you can have a video actually taken by the video camera. All of them will end up with multiple images that somehow need to be aligned. And, you know, sometimes the researchers joke about this and call them the axis of evil for super resolution after George Bush's phrase. And they say, well, there are three things that really give you a hard time. And, you know, they're much easier said than done. First of all, you need subpixel accurate motion estimation algorithms. And that's not trivial at all. You need to do deblurring, as we will see. And sometimes this deblurring is quite challenging. It could be spatially varying blur, because as you make these multiple captures, your blur can vary from one capture to the other, and even within a capture, it could vary. And then your models may be incorrect. You know, we all make mistakes in modeling. So how do we combat all of these issues? Well, there was a paper, which is considered a seminal paper back in 2004 by Lin and Sham. And Sham was at MIT. At that time, he was actually at Microsoft Asia Research. And this was the first theoretical paper that put some limits on how much can you expect to improve with super resolution. And they assume that you're doing local translation. And then they say, look, you know, in real life, there are all sorts of issues in terms of the diffraction limit of the lens, in terms of the, you know, the blur, the optical blur, in terms of the noise and modeling and all that. And they come to the conclusion that if you are only looking at local translation, you really cannot do, in a practical sense, better than 1.6x improvement in resolution. But theoretically, you could do 5.7x. So it's possible when you're simulating your results, you know, and publishing a paper, but when you actually get real life images and you try to super resolve them, you probably are closer to the 1.x if you're only looking at translational motion. However, the authors did admit that if you allow for higher order motion models, such as rotation, perspective transformation, or others, then potentially you could do more than 1.6x super resolution. However, the limits still are bounded. It's not that you could do infinite super resolution. This is a famous equation, and nothing is complete without having that equation that kind of summarizes all the uncertainties that they look at. And of course, I don't expect anyone to make any sense out of that equation. It's just a famous equation that everyone quotes in their paper when they refer to the Lin and Shum paper. So let's just summarize the super resolution model, and then I will show you some images, okay? So essentially, working with a well-known image, which was digitized by the University of California, USC, Southern California, in 1977. It's called the Lena image. Imagine you start with a high-res scene. Let's call it X. That high-res scene could go through a geometric transformation, right? Let's call it M. This is for the kth observation, because we're going to have multiple low resolution images, right? So the kth one is going to have its own geometric transformation. There will be some kind of an optical blur. Let's call it B sub k for that kth observation. There will be some kind of a downsampling. In this case, the example is just a 2x downsampling. Maybe it's a 4x downsampling. Depends on the problem. There is also noise. Let's call that N sub k, which would be different for each realization or each frame of video that you capture. So you end up with this low resolution observation Y sub k, and what you really want to find is X, which is all the way to your right? So you can mathematically, and it's easy to derive the mathematical formulation. Y sub k is the cascade of the downsampling, the blur, and the geometric transformation on X, plus the noise. You could lump together those first three, the downsampling, blur, and geometric transformation, into a single kernel called W, and there you are. You have YK equal to WKX plus NK. What do you know here and what do you not know? Well, this is your observation model. YK, of course, are these low resolution images. You have M captures, 4, 10, 15. X is the original one. You need to calculate it. This is your holy grail. This is what you're looking for. The motion warping matrix, unfortunately, you have to estimate it. It requires subpixel estimation. That's tough. The blur model, sometimes it's known, sometimes you have to estimate it. Could be very tough. The downsampling matrix, usually dictated by the required resolution, so it's fair to assume that it is known. Noise, of course, the noise is not known, otherwise it wouldn't be random, but the statistics of the noise are known. So this is what people used to work with, okay? Now, the seminal paper, which kind of forms the latest advancements in reconstruction-based super resolution, is by 4 people. Farsiu, Sina Farsiu is now a professor he was a student at the time, a Ph.D. student at UC Santa Cruz, and one of the co-founders of that Motion DSP company, a picture of which I showed you. Sina is a professor at Duke University. Ilad is a professor at Technion University, and Peyman Milanfar is used to be a professor at UC Santa Cruz. Is now a researcher at Google, leading a large group of people working on similar kind of problems. So in practice, the noise may not be exactly white, motion estimation may not be accurate, and everyone was looking at L2 norm energy function so that they can create the regularization and solve it, okay? But these guys, they essentially showed that an L1 norm, and I will say a few words about that, what L2 norm and L1 norm means in a moment, but let me summarize their contribution. They essentially looked at an L1 norm. Within our own department, for example, Dr. Markopoulos has made significant contributions to looking at L1 norm or even lower P norm of tensors. And essentially the difference between L2 norm and L1 norm, as I have in the next slide, is how you define your regularization. Imagine I have a cluster of points and I want to represent that cluster with a single number. What do you think that single number should be? Should that single number be the centroid or mean of the cluster? Well, then you're minimizing the squared error. That's an L2 norm. Or should that cluster representative be the median, where half of the points are larger than that, or essentially what minimizes the absolute deviation rather than minimizing the squared deviation. Well, that's L1 norm. Why is L1 norm sometimes better? And if it's better, why is L2 norm used? Well, L2 norms is mathematically much more tractable, okay? So people like the L2 norm. But L1 norm, especially when you have some measurements where you may not trust all of your measurements or your model parameters, L1 norm is more forgiving. Why is that? Because look at mean of a few numbers. If you change one of the numbers, one of the outliers, the mean changes significantly. But now look at the median of those numbers. If you change one of the outliers, the median does not change. So the median is insensitive, or the L1 norm is insensitive to mistakes that you might make in your estimation of parameters. And mistake is the name of the game when you deal with super resolution type of estimation. On the other hand, you expect that it would be mathematically more difficult to work with L2 norm. So they have several methods. Let me show you some examples. You can, by the way, I will show you where to download this code and run your own images, okay? So this is an example that they report. 20 images, resolution enhancement with a ratio of 4x. So we're going to do a 4x enhancement. This is based on the old paradigm of L2 norm super resolution. It looks better. Clearly, you know, you could read some numbers that you couldn't do before. But look at the L1 norm, the results that were reported in their paper. Clearly, the L1 norm in this case works much better, right? The image to the right. You can download a MATLAB version of this code, which there are several versions of it. You could go to the UC Santa Cruz website, but actually the code that was written as a graduate project by Oded Hansen, I think is better. So you can download that from this, and you could do your own images. These are some more images that were reported. Here are 8 low resolution captured frames. This is using L1 norm with a total variation bilateral regularization, which we're not going to get into, but for the sake of completeness, I have there. And look at this. This is a license plate you're trying to read, and there is the super resolved license plate. Or here is another example of text that you would like to read, and here is the super resolved text using, again, all of these were done by downloading Oded Hansen's code. And as I said, you could experiment with your own images, okay? So then, you know, at the turn of the century, literally at the turn of the century, the face hallucination paradigm came into the market. What does that mean? Face hallucination is a special type of super resolution that pertains only to faces, because faces are so important, right, in surveillance kind of applications. This is an example of face hallucination, not the seminal paper by Simon Baker and Takeo Kanari at CMU. Rather, this is a few years later at MIT with Professor Bill Freeman. And by the way, Lin and Sham that I mentioned from Asia Research Labs, Microsoft Asia Research Labs, Sham and Freeman did a lot of work together on face hallucination. So look at the image to the left. That's a typical low resolution face, right? And the hallucinated result, which is what Freeman and the co-authors at MIT reported. And you can, by the way, go to this website that I have listed down here and see all of these results for yourself. You could see that result, and then the original face, you see some artifacts there. That's mostly because of the JPEG compression when enhanced within the PowerPoint, but that's the original face. You know, they're not exactly the same, of course, but that's remarkable, you know, that you were able to get this result from a single image. This is not based on multiple resolution, multiple frames of low resolution. This is a single image. So when did the regularization come from? It came from example-based techniques, okay? How does face hallucination work? You know, I like Einstein's quote that says everything should be made as simple as possible, but no simpler, okay? If I try to make face hallucination as simple as possible, but no simpler, this is what it will look like, and it will not make any sense to you. But, you know, I have to just put it down here for sake of completeness. So the part that is easy to see is that it needs a large collection of other high resolution face images. Well, the part that cannot be made any simpler is that there is two contributions within face hallucination of the MIT work, the theoretical contribution and a practical contribution. The theoretical contribution looks at a maximum a posteriori or a map solution of a two-step statistical model that integrates both a global parametric model and a local non-parametric model. Exactly, this is what you get when you listen to Einstein. And the practical contribution is a robust warping algorithm. You could, of course, read about all this at the website and for those people who are interested. But most people are interested in seeing exactly what can I expect, right? So let's look at some images. Here are some images that are reported by Bill Freeman's group, right? The image to the three images in the left column are the input face. They are 24 by 32. Using their terminology, the next set of images is that global inferred face, right? You're not there yet, then you put in your local model that starts fine-tuning things. And then this is the hallucinated result, right? The third column. And the original high-resolution face is to the rightmost column. So let me take out column B because that inferred global face really is an intermediate step. You essentially are looking at the face hallucination results, the column all the way to the left versus the center column here. That is what face hallucination can do for you. How good is that compared to the original face? Well, then look at the face to the and the right column, okay? So now we kind of switch to the second part of our presentation, and that is looking at the deep learning based techniques, okay? What made deep learning feasible for images and video? Dr. Patucha provided some of these numbers for me. Ray and myself used to be colleagues at Kodak, and then, you know, he was at the computer engineering department of RIT. Now he's at Apple on leave. And he is the expert for deep learning. He teaches multiple deep learning, machine learning courses. But look, in the turn of the century, in 2010, the fastest graphic card was 1 teraflop. Now it's 29.77. I rounded that to 30 teraflops, and it only sells for $699. In fact, Ray tells me that the state of the art is somewhere between NVIDIA 3080 and 3090. And that's this information is from September of last year. That's how fast things are changing. There are deep layers, okay, more layers in neural networks. The very popular architecture called YOLO version 3 has only 50 layers. And I said only. Why? Because some networks have close to 1,000 layers. And these layers are densely connected instead of sparse model through convolutional networks. And there are some advances in neural learning models like the ReLU activation function, batch normalization, Adam optimizers, all of which are topics of, you know, courses. And of course, I cannot make them any simpler, as Einstein says, but they all have made contributions to the 10-year or a decade of advancements in deep learning. And look, there are also large and diverse training image data sets. ImageNet, okay, which is a large database, has 14 million images. The Celeb A, which is a database of celebrity face images, and I will show you that, not the database, but results based on that for face hallucination of celebrity faces. It has 200,000 celebrity face images. Go and visit these training sets. You know, they're open to the public. You could see easily, you know, what the size and the magnitude of these are, okay? So if you look at the paradigm of super resolution using deep learning, things change. People don't look at multiple frames of video. People look at two things, and it's very important to actually make the distinction between the two, okay? Number one, that there are techniques that improve the resolution of a randomly chosen single frame low resolution image. Remember, I told you that this problem is very ill posed, right? And it needs regularization. Regularization in this case comes from training the network with many, many millions example images, okay? That's what the regularization is. But essentially, if you want to grab a face or any image for that matter that is low resolution from the web, and you want to create a higher resolution version of that, then if you have a network that has been properly trained on similar, not the same, but similar images, okay, you expect to be able to get a good result. There are 3 more recent results, one of which I will just show you in the interest of time, because I have about 20 more minutes left. One of them is residual dense network. I'm not going to talk about that. I have it as part of my appendix. The other one is the residual channel attention network, which again, I will not talk about, but you will see that these are the leading technology kind of seminal papers. The one that I will talk about is super resolution based on a generative adversarial network, or GAN, because they are so popular. The GANs are used to make fake videos, like the deep fake videos are all made based on GAN. So this is one paradigm, okay? There is another paradigm which didn't even exist with the reconstruction-based algorithm. The second set of algorithms, or this alternative paradigm, is what people call an encoder-decoder paradigm, or like a task-aware or a content-aware paradigm. You start with a high-resolution image. So unlike the first case, you do have the high-resolution version of the image. You create a low-resolution image using a very specific deep network. We call it the encoder network, okay? You will see some very interesting examples of that in a few minutes. And then that image looks just like any low resolution image, but beware, it's not just any low resolution image, because if you take that low resolution image and you try to super resolve it with the decoder network, which is matched to the encoder network, suddenly you get wonders, okay? That low resolution image can turn into a high resolution image with a lot of detail and with practically no other input required. So you say, well, of course, because the network has been trained on that image. No, the network has not been trained on that image. The network has been trained on similar images. And I will let you be the judge, okay? I will train the network on similar images, and then we will use the network for images that are totally outside the training set. And the whole network really has a footprint that is smaller than a high definition image, okay? So it's not a big network. It's about 6 megabytes, okay? And a HD image, uncompressed HD RGB image is 6 megabytes, okay? So the footprint of the network is small, yet you can run that network on these low resolution images and get really pleasing high resolution images out. We will see that in a moment. There are 3 papers that are all, as you can see, the publication dates are so recent, right? Task aware, that refers to encoder-decoder matching, or the encoder-decoder paradigm, or the learned image downsampling, or content adaptive sampling, because these are all aware of the high resolution image, and purposefully that high resolution image is turned into a low resolution image. But the one that we're going to talk about, and this is what my PhD student Prasanna actually chose, this is the paper he chose to report on for his qualifier exam that he took a couple of months ago. So we have a lot of results that he has generated himself. I will give you a pointer to all of his results, to his code. You can download those codes. You can run it on your own images. You can practically duplicate everything that you see here and more on your own images if you're interested, based on the pointers that I will give you. So the 2 papers that you see in blue are the ones that I will talk about. I will start with the super resolution using the GAN, which is essentially working with any low-res image you get off the net. And then I will end my presentation with the IRN network, which is a task-specific or an encoder-decoder optimized kind of coder. So what are generative adversarial networks? You've probably heard of it if you don't even work in the area of deep learning. GANs are practically what are responsible for the deep fakes, okay? They are based on a pair of neural networks that compete against each other. That's where the name adversarial comes from, okay? One network is called the generator network. The other network is called the discriminator network. The generator network tries to fool the discriminator network, and the discriminator network is trying to call the bluff of the generator network. It was actually invented by Ian Goodfellow, okay? And Ian, after graduating, he was at Google X for a while. For the last few years, he's been working with the Apple on special projects division, where, you know, it's very hush-hush and you don't know what they're doing, but they are working on the most disruptive kind of research technologies. You know, as an aside, those of you who are mathematicians, you're probably familiar with the Erdős number, right? Erdős number is a degree of separation type of number. Paul Erdős, spelled E-R-D-O-S, was a Hungarian mathematician, a very prolific and a very famous one. So people always kind of measured their degree of separation from Erdős by what they call the Erdős number. So Paul Erdős himself, of course, has an Erdős number of 0. Then someone who has published a paper with Erdős has an Erdős number of 1. A person who has published a paper with someone who has published a paper with Erdős has an Erdős number 2. Believe it or not, I have an Erdős number of 5. And you know when I found that out? I actually found it out this afternoon. I was talking to Dr. Nate Cahill at the mathematics department, and he told me that he has an Erdős number of 3, and he has published a paper with Dr. Ray Petucha from computer engineering. So Ray has a Erdős number 4, and I have published a paper with Ray. So I get an Erdős number of 5. I mean, I'm really proud of that. If you are more into the entertainment industry, you can look at the Kevin Bacon number, right? The Kevin Bacon being the prolific actor, the same thing, degree of separation. So why am I mentioning all this? Because I kind of have a weird degree of separation from Ian Goodfellow, the guy who came up with the GANs, probably one of the most innovative networks in modern deep learning. How is that? Well, I shared a household for 18 years with my son, my older son, who shared a classroom with Ian for 4 years at Stanford. Both of them were the undergraduate class of 2008. So my Ian Goodfellow number, if you will, is 2 in that sense, if you indeed count it as a separation, degree of separation. But anyway, humor aside, GANs are the leading technology for producing deepfake videos. Let's see how GANs have been applied. Again, I don't expect anyone to follow this one slide. It's one of those, again, Einstein quotes that everything has to be made as simple as possible, but no simpler. I know everyone wants to see results, right? So this is how the network works, but let's look at the results. Okay, so you can actually watch this on YouTube, because this was a presentation made at CVPR and back in 2017, and it's on YouTube. It's a 12-minute presentation. You could, of course, download the paper as well, but the presentation is more fun to watch. And if you look at the image to the left, okay, this is a low-resolution image that has been 4x upsampled with bicubic, which is the most common traditional signal processing technique for upsampling images. And then you are looking at the middle picture, which is the super resolved picture using GAN, generative adversarial networks, okay? And the original, of course, which is better, is to the right. But remember, this image was not part of the training set. How was that trained? We will see that in a moment. This is some phase hallucination results, right? This is again from the recorded CVPR presentation. This is a 16x super resolution. The network has been trained on Celeb A image set. Celeb A image set, I really recommend anyone who likes data sets to go and check out. Just Google Celeb A data set. It's 200,000 celebrity faces. And the network was trained on that. And then you try to super resolve these images. Look at the image to the left and the image to the right. Those are the two images that you want to look at. That is what is inputted to the GAN network, and that's what's come out of the GAN network. Again, of course, there's a lot of information in the training, but as long as training is done on similar type of images, face images, then you expect to get very good results, okay? But beware, if the images are not part of your training set, and of course, you know, the authors are fast to report this. They admit their shortcoming is that you may not get a good answer. Look at the image to the image to the left. That's a bicubic 4x upsampling, right? You can hardly read the text. It's not readable. But look at the GAN image, which had been upsampled. It's not good either. Why is that? Even how to do everything with, you know, some of the text here, or the Ellen Finkelstein, you know, writing down here, it did not reproduce well. The faces were so impressive, right? But this is not impressive. Why is that? Look at the original to the right. The reason is because the text kind of images were not part of the training set. They actually trained it on 350,000 different randomly chosen images from the test, that's ImageNet test set, but images of a text were not part of them, okay? So now let me talk about the final part of our presentation. This is the invertible network, okay? This is what my student, Prasanna, actually worked on, okay? And this is something he did for his qualifier exam, okay? So the GAN-based or the RCAN, which I didn't discuss, those methods, they work on any single low resolution image, right? Even though the image is, or the problem of super resolution is very ill-posed, they essentially do the regularization through example-based algorithms, okay? The only requirement is that the network be trained on similar images. And you saw what happens when it's trained on similar images, not the same image, but similar images. But you also saw what happens when they are trained on images that are not at all similar, right? Like the text image did not work well. But the encoder-decoder paradigm is a totally new paradigm, okay? This is only a few years old, literally 3-4 years old. The encoder-decoder paradigm, it starts with a high-resolution image, okay? And then it generates the low-resolution image using a specially designed deep network encoder. I will show you some very interesting examples in the remaining slides, okay? The remaining 10 minutes. And then upscales the low resolution image using a matched, and the keyword is matched, that I have put it in red, deep network decoder. Now, let's stop for a moment and digest this, because you might say, okay, so you have an encoder that downsamples the image, so I can make this image available to everybody. They can put it on their phone, they can put it on their local whatever computer, and if they want to go to a higher resolution version of that, they don't really need to go and download the higher resolution version. They can just run it through the matching decoder, and voila, comes out a high resolution image. The answer is yes. And of course you say, well, that's kind of too good to be true, right? This decoder network, did you train it on that image? Well, you be the judge. I'm going to show you that the decoder network is trained on some 800 images, and I'm not talking millions, really 800 images. And then I use, or Prasanna has used images that are totally outside the training set, and you will see similar results will still hold. And then you say, well, in that case, what's the footprint? Is that some app I can put on my cell phone? The answer is yes. The footprint of that is about 6 megabytes, okay? If you put that decoder on your cell phone, it will take as much space as a HD resolution image, which is uncompressed, will take on your cell phone. So, you know, it's really good stuff, okay? So if the decoder network is used to upscale a low resolution image that has not been downscaled by the corresponding encoder, the results could be quite disappointing, as I will show you that, okay? Encoder-decoder techniques would allow transmission, storage, sharing of low-resolution images that could be upscaled efficiently locally, okay, on your phone with a matched generic decoder. It doesn't have to be, again, a decoder that has been optimized for your image, of course. It's a generic decoder without the need for additional information. Let's see how it works, right? I mean, a picture speaks 1,000 words. So let's do that. Let's start with an original image, okay? Why are we using this image? Because everybody else is using this image. So in order for us to be able to report from these papers, we have to use that same image, okay? Here is a conventional downsampled version of that, okay? It says low resolution, 2x downscaled using conventional resolution reduction techniques like bicubic, okay? Now, that image, if you try to super resolve that without help from anything else, is not gonna super resolve clearly, okay? Use a bicubic interpolator. And of course, this is what you get. You know, the detail is not there. You cannot create something out of nothing, right? Now, look at the center image. I want you to put your attention on the center image. I am going to replace that center image with a low resolution image that has been generated by our network, okay, by the network we are reporting. The idea is that that low resolution image looks just like this low resolution image that you are looking at right now. In fact, you would be really, really hard pressed to tell the difference. There it is. You didn't see any difference, did you? If you saw, then you're hallucinating faces probably. But anyway, it's exactly more or less the same visually, not the same mathematically. Now, suppose that someone took this image, and this image has been trained with an IRN network over 800 images, not including this one, with 1.66 million weights, which, by the way, is a very, very small footprint, okay? Because there are networks that have 50 million, 80 million weights. And now, let's use the conventional method to upscale this image. It will look like the same garbage that I showed you before, okay? So if that IRN image is upscaled with a bicubic interpolator, no one can tell the difference between the original low resolution upscaled versus the network generated low resolution upscaled. But wait a minute, now I am going to upscale this image with, let's say, my phone, which has this generic upscaler or decoder. Now look at the image to the right, okay? This is the image that you get. Looks almost like the original. Is it identical to the original mathematically? The answer is no, it's not. But is it visually identical to the original? The answer is yes. Well, it cannot be mathematically identical to the original, because then you will be violating some kind of a principle, right? Some kind of a physical principle, because the low resolution image, it could be any low resolution image using a network that is generic network, only has 1.66 million weights, which is almost comparable to the size of the image here, cannot generate the original mathematically identical image. That would be a violation of some principle, right? But the fact that it can generate such a nice looking image is remarkable, right? Now look at the ordinary low resolution image. In fact, let me go back. Look at the image to the right again. If I took the ordinary looking low resolution image and I used it with my network, it will look like the same, again, garbage that it used before. So it has to be a matched encoder decoder paradigm, right? But the idea is that if you use that paradigm, then you are going to be getting very, very good results. Okay, so you say, well, show me that PowerPoint example, right? The one that the adversarial network, the generative adversarial network did so poorly on. You know, clearly we have not optimized this particular network with the text images, but look what happens. This is the low resolution version upscaled with conventional techniques. This is the low resolution version that was generated with the network. Again, not trained. Network is trained on something else, but the low resolution image was generated by the network, and that low resolution image looks just like any low resolution image, then was upscaled by the matching network. You could see the huge difference between the two, and also the difference between this content aware or encoder-decoder matching super resolution and the adversarial network, the generative adversarial network, or the GAN. Okay, now if you push this too much, try to do a 4x, then of course you're gonna see some problems, but not as much as you would have seen with any of the other ones. Okay, right now we upscaled it with a 2x upscaler, and that's why the results were so good. And but if you try to upscale it twice, then of course, you know, results start degrading. Now, how does this work? Let me try to explain this in 4 minutes, because that's as much time as I have for my 1-hour presentation. Okay, the way that it works, and I'm going to try to make it as simple as possible, but no simpler, right? We start with an original image, and we go through this invertible rescaling network. What comes out of the network, it's invertible, okay? Invertible means mathematically invertible. So it can't be just a downscaled image that comes out of it. There are 3 what we call residual images coming out of it. You say, oh, wait a minute, you didn't tell us about these residual images. Okay, of course, now I can see some kind of a wavelet decomposition. You get this downscaled low resolution image, you combine it with those 3 detailed images, and of course, you're gonna be able to get an upscaled image. Yes, this is what I'm doing right now, okay? That's how the network started. The network started by doing a invertible, that's where the name comes from, an invertible downsampling. And of course, in order to be able to invert it, you need auxiliary information, right? You need that additional information that you see on the top. But now let's do something interesting, just like, you know, Penn and Teller do when they do their magic tricks, right? Right now, mathematically identical to the original image because the network is invertible. Now let me look at the distribution of the pixel values within those 3 detail or what we call residual images. They look Gaussian. Guess what? Let's get rid of them, okay? If we get rid of them, of course, if I feed back the image, the downscaled image, into the network, I'm going to get garbage, right? I need those high detail images. I just got rid of them. So what am I going to do? Well, the way that the network is trained, because the distribution of those images is Gaussian, let me just randomly generate a Gaussian number, and just synthetically, this is purely synthetic, can happen in a jiffy, and all that it needs is a random number generator that generates a Gaussian random number with mean 0 and variance of 1. That's it, okay? So I replaced the case-specific, listen, the case-specific images to the left with the case-agnostic images to the right. Okay, and I won't be able to do that ordinarily unless the network has been trained very cleverly. And that is really the main contribution of the authors, that they have been able to define their loss functions in such a way that when the network gets trained, then you could get rid of your actual case-specific detailed images, replace them with case-agnostic random number generated images. And to just phrase that, the case-specific high-frequency image is replaced with a case-agnostic latent image that can be generated with a simple Gaussian distribution. No storage overhead, can happen in a jiffy. So now what am I feeding into the network? I'm feeding the downscaled low resolution image, okay? You don't see that on your phone. As far as you're concerned, when you say upscale on my phone, it's taking that downscaled low resolution image, but under the hood, it's generating those Gaussian random numbers, okay? Just a seed is all that is required, and then feeding the low resolution image alongside those detailed synthetic Gaussian details, and you get the same image. Is that mathematically identical like it was before? No, it's not mathematically identical, but that's the beauty of the technique, because as I said, if it was mathematically identical, then you will be violating some kind of a principle. Okay, so now let's look back at this. You've already seen this example one more time, but now you probably will see it with a different eye. Okay, so we start with an original image. We downsample that image with a encoder network, okay, with an IRN network that has been trained with a footprint of only 6 megabytes and only been trained on 800 images. Okay, then we take that low resolution image alongside a case agnostic randomly generated set of numbers, which you will never see because it's under the hood and does not require any additional information. And then we upscale that image to get this beautiful looking image that almost visually almost 100% matches the original image, but of course mathematically is not the same. So my last 2 slides are essentially just what are these invertible networks. I'm not going to go over that, but you know, for people who are interested, because I will make a copy of these slides available for everyone, I will give them to Dr. Liu, and he will post them wherever you post the presentations for Image Science Seminar Series. But the last slide, and this talks about the weights that I am interested in, is that my student Prasanna, this is my last slide, has implemented this algorithm as part of his qualifier exam, and not only has confirmed the reported results, but also generated the above results on data sets that are not reported in the paper, okay? He has put his code in this particular folder, and you can download, go get his code, okay? Show you some images that he has, okay? Actually, let me show you this. I think this would be even more interesting because this is an image that is not only is not in the training set, but was not even in the data set that the authors reported, okay? So this is Prasanna's image. If you do this is a cropped version of a bigger image. And the reason we have cropped it is because I want you to see the detail, because you know, FBI is always interested in reading that license plate, right? So the 2x by cubic method will give you this, whereas the 2x invertible network, upscaling, downscaling, matched network will give you this. And this is the original. So it's really hard to see the difference. They're not mathematically identical, but it's hard to see the difference between that and the original. And I think, you know, we've taken about almost just under 60 minutes to do this presentation. So I appreciate your patience, but I think we are good now, and we could open the talk to any questions. The arrangement that I made with Prasanna, like every fair advisor, is that I will answer all the questions on the Blade Runner movie, and he will answer the rest of the questions. So I hope you still will adhere to that. Thank you all.
Thank you very much, Dr. Rabbani. And for the general audience, do you have any questions? And you can freely directly speak and ask the question, or you can write in the chat and the chat channel, and I can read the questions for you.
Hi, it's a very interesting presentation. Thank you very much. I have a question. So first, like this IRN network. So as I understand, I just want to make sure I understand it correctly. If we will try to decode this image on different devices, let's say like different phones, even though we will have results visually similar, mathematically, even those upscaling images would be different.
Yes, they would be different because every time you use the random noise, you generate a mathematically different image.
Yeah, and another question, basically like based on the last slides with those plate numbers. So like in the first place, we have those low resolution images because we have like, I don't know, like upscaling something that wasn't, that didn't go through this particular decoding, like encoding network. So what are real life applications you can see except of like transmission, like data, like image compression without visual losses?
Prasanna, do you want to take this or should I answer it?
You can go ahead.
Okay. Well, compression is my forte. You know, I was the JPEG and MPEG representative for Kodak for some 25 years. And in fact, what we are looking at right now is maybe application of this to compression. Okay. Because as you say, the main advantage of this is not as much for super resolution, right? Because if I just take an image off the net and try to super resolve it with the network, if it's not a match encoder decoder image, it's not going to really give me a super resolved image, right? However, aside from the fact that people can locally enhance the look of the images, you don't have to download high resolution versions of things. Aside from that, it has some applications to compression. And what we're going to look at, depending on what direction Prasanna's thesis will take, is that we say, okay, what if we use this high resolution image, which is not mathematically, of course, identical to the original high resolution image, but as Prasanna said, if we know exactly what the seed is, for example, we could just generate that random number each time. That only takes one input, right? And then find the difference, the mathematical difference between the original high resolution image and the visually synthesized high resolution image, and then see exactly what the information content or the entropy of that residual or difference image is. And by using sophisticated coding techniques and context modeling, hopefully be able to get a more compact representation of image pyramids in terms of the total number of bits that are required to keep them. That's a very, very good question. In fact, that's the future direction of our research.
Okay, thank you very much for answering. It was a really good presentation. Thanks a lot.
Yeah, thank you, Igor.
I've got maybe a similar question. So the same thing, because you're the encoder part of the network must rely very much on which those 800 images were that were trained. So in the examples you've shown here, where this was a synthetic image, was this network trained on synthetic images? Was it trained on a group of random images? How important is the set of training images, and how broad can you apply this? So for example, if you were going to use this to allow faster downloads of videos, would you have just one encoder and people could have the decoder network for this? Or would you use one for one kind of movie and one for animations?
Yeah, that is an excellent question, Jeff. That's a Prasanna question because he's done all of the training, and I will leave that to him to answer.
Yeah. So firstly, in the invertible network, encoder and decoder is the same. Okay. And the training is done on 800 div 4K images. So these are natural images that we can find. And these, according to the results, they generate fairly good results on text, on everything that is not seen in the training set. So we can just have the single invertible network on all the devices for both encoding and decoding.
Yeah, Jeff, the nice thing about this whole thing is that Prasanna has created a framework for training the network you could essentially, I think any of the students who are listening to this, for example, if they're curious, they could easily access his area and choose their own set of images for training, and then use their own set of images for testing. The trick is in the loss functions that the network uses, right? They use 3 novel loss functions. One of them is what they call the low resolution guide loss function. In other words, because if they just forget that and try to create any low resolution image so that when it's upscaled, will give you a good high resolution image, then the low resolution image might look like garbage, okay? They want to make sure that the low resolution image is as close to a bicubically resolution reduced image, right? So that is there are 3 loss functions. That's one of the loss functions. The other loss function, of course, is to try to minimize the error between the high resolution reconstructed version and the original high resolution version, right? So that's the second loss function. And a third loss function is try to make that residual image, those images that we replaced with the randomly generated, Gaussian, try to make it adhere to a uncorrelated, randomly generated set of Gaussian points as possible. So of course, these 3, kind of are in conflicting requirements with each other. And part of the training of the network is how to balance all that, okay? But the paper is available. Prasanna, as I said, used that for his qualifier. And the training is, all of these things are real. It's not like, we are reporting on something that somebody did sometime and no one can repeat it. This is as fresh as it gets. The paper was published last year, and all of the results and the training is available through Prasanna's folder. So I actually encourage everyone to kind of dabble into this, and it's fun, and try it out. But those loss functions are really the main contribution of the paper, and being able to train in a way that those loss functions are minimized and are balanced at the same time.
Thanks.
Dr. Rabbani, hi, this is Amir. I have a question and a favor. First of all, I was wondering if you guys can paste the link to in the chat, because it's easier to follow. I took a picture,
let me see
but I
the
think
chat.
it would be impossible for me to recreate the link by just looking at it.
Let me see if I can access the chat here. Hold on. Did you send us a chat recently?
I did.
Okay, let me see. Let me actually stop sharing. That will give me, oh yeah, there it is. Okay, I can see it. So how could you create, no, that's Dave Mantle, right? Which one was your chat? I'm sorry, I'm trying to.
Oh, I didn't send anything regarding to the link. I was just asking if you guys
I like your comment, by the way, that it's $6.99 if it's in stock, right? And I see, yeah, Miguel, you have an Erdős number of 4, okay, but maybe my Kevin Bacon number is better than you. I doubt it. Okay, yeah, go ahead. I'm sorry.
Yeah, no worries. And my question would be that is this transferable to the domain of denoising? Because I know autoencoders are used a lot in denoising, but I don't know if the lower dimensionality in the bottleneck could be a restriction to the denoising application.
Yeah, that's a good question. I'm not qualified to answer that question because I'm not a machine learning expert. I will defer that to, if I knew that Ray was trying to call in from Apple, but I don't know if he's online. If he is, I would ask him to answer that question. If not, maybe Prasanna can address that question.
Yeah, I did try to do denoising application using this invertible network, but I didn't have any straightforward success in it. Because of the invertible nature, like whatever you input, you get the same input, right? So if you were to input a noisy image, you still get the noisy counterpart. So it is a tough application using an invertible network.
Okay. So okay, my assumption was that it would take in a noisy image, but it would make it less noisy. That was my assumption.
Yeah. So maybe the low resolution image is noisy and the high resolution image is not noisy.
Well, it doesn't have to be low resolution. It could be any resolution. And well, yeah, it could be any resolution, and then it has some noise to it, and the output would be, again, any resolution, but less noise.
Maybe we have to try that.
Yeah, that sounds like an interesting. Yeah, you know, we haven't really defined a direction for the thesis yet. So I actually welcome all of these questions because you know, maybe you could inspire us with some of the you know, directions to take from this paper here.
Thank you.
Thank you, Amir.
Professor, we also have additional questions in the chat.
Okay, you want to go ahead and answer them, Prasanna?
Yeah.
They are not about the Blade Runner movie, so I defer them to you, okay?
Yeah. How could you create decoders of different quality? Yeah, Professor, do you have the slide where we can show where we can do super resolution for different resolutions? So you just stack the decoders in series.
Okay, hold on. Let me
so you can do 4x and 8x.
Which slide do you want, Prasanna?
Just the invertible network slide.
Okay, hold on.
Yeah.
So you want this one or the next?
Yeah, this one, above one. Yeah.
Okay.
So we can just, this entire downscaling 2x downscaling module. So if we have a bunch of them in series, we can progressively downscale it to 4x and 8x and so on. That's how you can have different sized reconstructions or different sized images, downscaled images. Which measure best captures strengths and limitations of the model? Yeah, currently we're just looking at signal to noise ratio, and the other one is structural similarity. Maybe we can have a metric where we can use people to judge which images look better. Mathematically, we just have those two metrics right now.
So, you know, the peak SNR is, for example, what I'm pointing at right now, 41.9, and the structural similarity index is a number between 0 and 1. SSIM, which is Albovic. Albovic, by the way, is a star or super graduate of Tom Huang, the person whom I mentioned who sadly passed away last year. So Albovic at UT Austin, who came up with the SSIM index, is another of 120, I think, PhD students who graduated from Tom Huang. But yeah, the SSIM index and the peak SNR is the ones that we actually have right now.
Any other questions?
Well, thank you so much. These have been great questions, and thank you for your attendance. You know, everyone's time these days is so precious. So we are both really humbled and flattered by your attendance of our talk.
So Amir is asking to put the link in the chat channel actually.
Yeah. Yes, I just did that.
Yeah. So, Dr. Liu, you can tell me later. I would be more than happy to make this presentation either in PowerPoint or in PDF available to you know, your participants. So let me know how the process is. And because there are a lot of links in here to some of the results that we generated and stuff like that, even from the more traditional techniques, anyone who wants to repeat those or see them, I'll be happy to share with them. But I'm hoping to be able to put this presentation in some kind of a repository so that people can access it.
Sure, yeah. I will try to deal with that, yeah. So the last call, if there's no other questions, and we would like to thank Dr. Majid Rabbani and his PhD student, Prasanna again, and for their excellent talk. And definitely, if you have any other questions, and I believe Dr. Rabbani will be happy to answer by email or whatever other thing.
Yeah, exactly. You know, any questions are actually welcome because, as I said, they will be inspiring for us. for future directions. Thank you.
Okay, great. Thank you very much, Dr. Rabbani.
Thank you all.
Prasanna.